All right, guys. So before we get started, before we start today's lesson, are there any questions over the homework? Any of those that you want to see work? Okay. Because what we're starting today is addition and subtraction, adding and subtracting two fractions. And whenever we add or subtract two fractions, we need the denominators to be the same. We need like denominators. We need them to be the same because if they're the same, we can add or subtract the numerator with whichever operation we have. So if we look at the first one here, 7 over 4x plus 3 over 4x, we want to add these two together. Now, since both of the denominators are 4x, it means we can add these two together. Since the denominators are the same, we can add the numerators. Now, since it is addition, we don't really need the parentheses, but we can include them. Just to signify these are two different expressions, and really we can say that we do have 7 plus 3. And 7 plus 3 is 10 over 4x. Questions on this so far? Now, as we look at this here, the numerator, we do not have addition or subtraction. The denominator, we do not have addition or subtraction. So we can simplify this 10 over 4 because there's a greatest common factor, or a common factor between 10 and 4, which is 2. And if we remove that, we simplify that out, it's going to reduce the top to 5 and the bottom to 2x. And we can do that because there is no addition or subtraction, it's just multiplication. So really what we're doing, we're not specifically saying it, is on top we have 2 times 5 over 2 times 2x. The 2 over 2 reduces, leaving us with 5 over 2x. Any questions on the first one? Let's look at B. 2x over x plus 6 minus 5 over x plus 6. Since the denominators are the same, we can subtract the numerators. If the denominators are the same, we can add or subtract the numerators. In this case, we can subtract. Now, we do have to be a little more careful with subtraction because that negative does need to be applied through every term in the second numerator, second expression. But here it's just 1. So really, we just say we have 2x minus 5 on top. 2x and 5, are they like terms? Well, no. And again, it'd be very tempting to want to go, these two x's will cancel out. They simplify out. But as we look at this here, on top we do have subtraction. So that 2x and 5 are stuck together. On bottom we have addition, that x plus 6 is stuck together. So for us to be able to simplify, for us to be able to reduce something, I need some multiplication to have stuff in common on top and bottom. But with our 2x minus 5 on top, there is no greatest common factor. There's nothing in common with 2x and 5. Nothing we can factor out, nothing we can simplify out. Same is true on bottom. X plus 6, there's nothing in common. There's no way to reduce it. And since there's nothing in common on top and bottom, we don't have the same expression on top and bottom. This is actually as far as it goes. We can't simplify further. It is 2x minus 5 over x plus 6. Questions on this here? Let's look at the next two. 8 12ths, 8 over 12x minus 5 over 12x. Now, 8 over 12x does have a greatest common factor of 4. But if we did simplify this, do not write this, down to 2 over 3x minus 5 over 12x, well, the denominators aren't the same anymore, which means we can't subtract. So really the first thing we need to do, since the denominators are the same, we're going to subtract the numerators, which is really going to tell us it's 8 minus 5 over 12. We can drop the parentheses and simplify from there. Well, 8 minus 5 is 3 over 12x. Now again, we might want to try to simplify the 3 and 12, but let's make sure we can. Is there addition or subtraction on top? No. Is there addition or subtraction on bottom? No. So there's nothing to say that we can't just simplify this 3 over 12. We can, because we do have that multiplication. We have that product. So we can factor that 3. We can simplify the 3 on top and bottom. The 12 on bottom is going to become 4x. What is the 3 on top going to become? 1. Because we still had a product on top and bottom, we can simplify. We can reduce it out. Question on number 1, how we got it to be equal to 1 over 4x. We ready for number 2? Since the denominators are the same, we can add the numerators. Really, we don't need the parentheses. We can just say 2 plus 1 over 3x squared. Well, 2 plus 1 is 3. Telling us that we have 3 over 3x squared. Again, we don't have addition or subtraction on top or bottom. So we can reduce the 3 over 3. And the 3 on bottom is going to simplify out completely, giving us just x squared. And the 3 on top is going to become 1. Questions on this here? You ready for the next one? 4x over x minus 2 minus x over x minus 2. The denominators are the same, so we can subtract the numerators. So we can put parentheses around it, but do we need the parentheses? No, we would definitely need it if the second term had more than one term. We'd have to distribute to the x and the 3. But here, since we only have one term each, this is the same. Now, the numerators are like terms. Yes? 4x and x. So what is 4x minus x? Almost 3x. Because 4x minus x would be 3x. We have 4 of them. We take 1 away. We should have 3 left. Now, we need to make sure this doesn't reduce. You're welcome. We can't reduce it farther. We can't cancel things out on top and bottom. Because if we look at the top, 3x, is there addition or subtraction there? But 3 and x, no, it's multiplication. So that means if there's something in common on top and bottom, there's a good chance we can reduce it out, yes? Let's look at the denominator, the bottom of this fraction. Is there addition or subtraction? Yes. Since there's addition on bottom, or subtraction on bottom, we can't say that x on top and that x on bottom cancel. Because that x on bottom is stuck with the minus 2. It is one expression. Now, we could have some simplifying that could work if there was a greatest common factor of x on bottom. Does that make sense? Then we could factor it out. We have multiplication. It simplifies. Here, that doesn't happen. Questions on 3 before we look at 4? The denominators are the same, so we can add the numerators. But really, do we need the parentheses? Well, no. There is no sign adjustment that needs to happen. We're good with this here, yes? 2x squared plus 2 over x squared plus 1. Again, be tempting to cross out the x squareds and x squareds. Is there addition and subtraction on top? Well, yes. Is there addition and subtraction on bottom? Is the numerator as simplified as it gets? 2x squared and 2 have a greatest common factor of what? 2. I can factor that out, yes? Now, if I factor the 2 out of 2x squared, we get x squared. When I factor the 2 out of 2, we get 1. Now, just because there's a greatest common factor on top doesn't mean anything in simplifying terms. It means that we can factor it out. It does not mean something's going to reduce on top and bottom. I think you've seen that number of times where we've solved it. Stuff can factor on top and bottom, it simplifies down, but it won't actually simplify out on top and bottom. Because factoring out that greatest common factor of 2 tells us we have 2 times x squared plus 1. On bottom, we have what? X squared plus 1 is still one term, yes? Now, we do have addition, subtraction on bottom, but really on top we have what? 2 times that x squared plus 1. We have 2 terms being multiplied together, yes? So can we actually simplify? Well, yes, because now it's just not purely addition, subtraction on top. We have this product, which tells me, yes, these whole terms can be simplified out, which is really just going to reduce this to what? Because I was able to rewrite the numerator as 2 times that x squared plus 1, we have 2 terms being multiplied together. The x squared plus 1 on top and bottom now can reduce. If it had been 2 plus that x squared plus 1, we still have addition. It still doesn't work because that 2 and the plus makes those stuck together. Yes? Questions on this here? Would it also be wrong to say normally up to this chapter, addition, subtraction, and normally been the quote-unquote easier, than more straightforward, the nicer ones to work with? Here, multiplication and division are the nicer ones to work with. They don't have as many rules to them. If the denominators are not the same, we need to get them to be the same. We need to find the first number or first expression where they are the same. And once we get them to be the same, then we can add or subtract the numerators. Now, least common multiple is what we look for trying to get 2 sets of terms, 2 sets of numbers, or more to be the same. Common multiples. It's been a while since we've talked about or you've talked about a common multiple. A multiple, we'll use 8. 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96, 104, 112, 120, 128. These are multiples of 8. Multiple is just a number added to itself different number of times. Every time we add 8, we get a new multiple. Because it's multiple versions of 8. We've seen this before, yes? Well, I can do the same thing with 14. 14, 28, 42, 56, 70, 84, 98, 112, 126, 140, 154, 168, 182, 196, 210, and it just keeps going on from there, yes? So if I were looking for common multiples, let me get a highlighter, of 8 and 14, we'd go through and see, oh, 56 is a common multiple. They have the same number. 112, 128, and there will be more going on out. We just have to go farther out to find them. 56, 168 would be the next one. But these are common multiples. 56 and 112 are common multiples. However, we would say 56 is the least common multiple. It is the smallest common multiple that 8 and 14 have. It is the first number we can turn both 8 and 14 into. Now, for numbers, it didn't matter a whole lot because we're talking purely about fractions. So 1/8 and 1/14, if we wanted to add them together, we would want the denominator to be 56 because it'd be the first number that they're the same. If we used 112, yes, it would get there eventually. We would get it to the simplified form, but we would have to take a factor or two out. There's an extra factor, there's an extra common factor that would have to be reduced. And for the most part, 30XS, graphing calculator can do those just fine, depending on what it is, because it's just numbers. We just have numbers. Calculators can simplify reduced fractions down very easily, very quick. It doesn't matter if we're using getting to the common multiple of 56 or 112 or 168. It can take those factors out. But when we start talking about expressions, x plus 4, x squared minus 2, the more we have, the bigger or more complex the number is going to be. Now, this didn't ask for the least common multiple of 8 and 14. It also asked for 16. So 16, 32, 48, 4, 64, 80, 96, 112, well, 112 is the least common multiple between 8, 14, and 16. It's the first multiple of all three that shows up. Questions on this here? All right, let's see another way to actually do this. Least common multiple also works on the factors. So we want to get this into the prime factorization. We want to see how many of each prime number are a part of each of these numbers here. So if we look at 8, well, what is 8? It is 2 times 4, yes? 2 is prime. What's 4? 4 is 2 times 2, yes? So we can say 8 is 2 times 2 times 2. Let's look at 14. 14 is what? 2 times 7. Come on. That's all we have, yes? It's just 2 and 7. 16 is what? 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. Okay. Questions on how we got 8 is 2 times itself, or 2 times 2 times 2. 14 is 2 times 7, and 16 is 2 times 2 times 2 times 2. We feel good getting here. Yeah. Because I know there's many, many, many different ways to talk about prime or least common multiple and how we get there. We can box, do a big L and put 8, 14, and 16 in there, and then put the common factors out to the side and then multiply together. But I think one of the ways to look at this with numbers is we'll start with any of the factors. So we have 2, 7, and that's it, out of any of the three. Those are the only factors that we see show up. So let's start with 2. And I want to take the number of factors, whichever one has the most. How many factors of 2 do we have here? We have 3. How many factors of 2 does 14 have? 1. How many factors of 2 does 16 have? 4. Whichever one has the most, that's how many 2's we take. It's great and all that 8 has 3. That's fine. But because 16 has 4, I want 2 as a part of the least common multiple 4 times, because it showed up 4 times in one of the sets of factors as one of the numbers, factors 4 times. We need it 4 times. It doesn't matter that 8 has it 3 times. 16 has 4 of them. We're taking 4. Then the only other factor is what? 7. And it shows up how many times? Once. Doesn't show up anywhere else, so we only need it once. Now when we multiply all of these numbers together, we'll get what the least common multiple is. Funny enough, 2 times 2 times 2 times 2 is, so we need to do 16 times 7. 2 carry the 4, 7 plus 4 is 16. On this here. Funny enough, what is the least common multiple of 8 and 16? 16. So really, we weren't so much looking at the least common multiple of 8, 14, and 16. Realistically, we were looking at the least common multiple of 14 and 16. On the graphing calculator, if we go math over to number, it'll do numbers. It won't do anything else. It won't do expressions, but it will do numbers. Does this make sense? Least common multiple with 9, 12, 15. And again, there's nothing wrong, absolutely nothing wrong with me going through and doing 9, 8, 27, 36, 45, 54, 63, 72, 81, 90, 99, 108, writing all those out, and then doing it with 12, then doing it with 15. Or I can break these down to the prime factorization. 9 is 3 times 3. 12, we can say is 2 times 6. And 6 is 2 times 3. And 15 is 3 times 5. So this time I've decided to write them in actual prime factorization form. We don't normally write it as 3 times 3, it's 3 squared. Now for least common multiple, we take which one has the most of each factors. So we can start with 2. 9 has 0 factors of 2, so we're taking none from it. 12 has 2. And 15 has 0. So 2 squared, we need at least 2 factors of 2, because it showed up at most 2 times as one of the sets of factors of our terms. Yes? Let's look at 3. With 9, it showed up twice. With 12, it showed up once. And with 15, it shows up once. So how many times do we need it? 2. Even though it does show up a grand total of 4 times across 3 numbers, how many does it show up in each one? 9 shows up twice, so that's the most we can take. Well, that leaves us with our last number, 5. It only shows up once. Now what do we need to do? multiply these together, yes? And realistically, at this point, we'd grab a calculator, tell it 2 squared times 3 squared times 5. 2 squared is 4. 3 squared is 9. 5. 4 times 9 is 36, and 36 times 5 is 0. Telling us that the least common multiple is 180. Questions on this here? And yes, especially when y'all first started learning this, this was challenging because, and it was for me too, but once I got my head around the fact that least does not mean small. We're not talking about numbers smaller than those. When we talk about least, we're talking about the first number going up that I can turn 9, 12, and 15 into. Because especially when we have the other expression, greatest common factor, we're looking for the biggest number smaller than those that goes into all three. So with least common multiple, we're not talking about smaller. We're talking about the first number that goes in all three. The smallest common factor of all three. We got to go up. Greatest common factor, we're talking about the biggest number that's divisible into all three. And that can be, especially if we think about it in terms of greater or smaller in reference point to the number. That's not what we're looking at. Questions on this here? Personally, I think greatest common factor, least common multiple with expressions is a little bit nicer. But the first thing we want to do with both of these is factor it. I won't even look at each of the expressions together. Let's look at them individually. Let's factor them as far as they will go, and then compare the two. So 4x squared minus 16. Is there a greatest common factor? 4. And if we factor 4 out of 4x squared minus 16, we get 4 times x squared minus 4. X squared minus 4 is something we like, especially with factoring, because it's going to factor to what? X plus 2 times x minus 2, or x minus 2 times x plus 2. If you want to signal or write some way to signify that is factored, because that's factored. X plus 2, x minus 2, there's no greatest common factor there. The degree of both of them is 1, so we're done. Let's look at our other expression. 6x squared minus 24x plus 24. Greatest common factor. 6. X squared minus 4x plus 4 will factor. Since the third term is positive, the signs are the same and match the sign of the middle term. So negative and negative. Factors of x squared are factors of 4 that we want. 2 and 2. And if we did check this, we'd get negative 2x minus 2x, which is negative 4x, the middle term we wanted, yes? So everything is factored, yes? Okay. Now I said I like this better than just straight numbers. Because with straight numbers, we're looking at multiples of each one. We're doing all of that there. We're looking term to term. I like this because factoring's, at this point, we're used to factoring these. We're not having to divide anything out. We do the process here, yes? One of the two ways I look at it is I look at one of the two expressions, not our numbers 4 and 6, the actual parentheses, and take everything from one and see what the other one has that this one doesn't. Or, let's just start at term per term. Our x plus 2's. The one on the left has one of them. The one on the right has 0. So how many will I need? 1, because it showed up once in one of them, so I need it at least once. x minus 2 on the left shows up once. On the right it shows up. So how many times do I need it? Twice. Because that factor showed up 2 times in one of them, I'm going to need it twice. And that's kind of why I like this a little better than the other, because once we get it in factored form, it's just x minus 1 showed up once there, shows up twice here, so we need it twice. Now all we're left with is what? 4 and 6. This is kind of nice because we can do it either way. The numbers are small. 4, 8, 12, 6. This is the least common multiple. Would putting x minus 2 on it work having 3 of them? Yes. Things will simplify, things will reduce. But the issue is that when we use more expression than what's needed, what's above this, they have to be factored out. They have to be reduced out. It also, any term, especially once we start solving, any expression, because we're going to multiply through the rational expressions to simplify the fractions out, anything we go above this least common multiple is another solution added in. There's another possible solution we're adding to the equation, which is fine. But if we multiplied through and got 3x squared plus 4x minus 6, this is the equation we have to solve, that's fine. We know how to do that, we're good there. But if we added an extra factor of just x, and that's just an extra x, no plus 1s, I've now made it a cubic, which isn't too hard to solve. We factor that out. But that extra x that I added in, x equals 0, which would be the solution, that solution would be a restriction because it's coming from the denominator. And we haven't got there yet, but anything I go above this least common multiple is going to add solutions that are restrictions. Which for this here is not bad. It's going to take me a second. That would be squared. So that would be 7 to take care of that. That would turn that into but with an extra x plus 1, we get to this here. Okay. I think we can say solving the top one's going to be a lot nicer than this. And because it's x plus 1, negative 1 is a solution. It's also a restriction. So we've made the problem harder on ourselves by adding those extra factors in. That's why, especially here with addition and subtractions here and there, but especially once we get to solving, being able to figure out that least common multiple is going to be huge. But I'm going to